Welcome to Empowered Learning. This will be the first video in the video series for the discussion about the cross-product operation for vectors. This video will go over the basic concepts and properties of the cross-product as far as the motivation for it, how we think about it in general. The second video that I will do will cover what the actual cross product is as far as how it's defined so that we can do examples. And we will do examples in the second video. The third and final video will kind of go back to more theory and actually show how it is that we come up with the representations for computing the cross product. And that will be both the form of the cross product that uses sine of some angle, as well as the form of the cross product that uses determinants. And so I will actually go over and give informal proofs on how that comes about. So before we go over examples in that second video, I did want to spend a little time talking about the cross product as far as its basic motivation, basic concepts, because we do need to know that before we actually use the operation. I am aware that, because I did this as a student as well, that I can actually learn how to be functional in the cross product operation and not really understand what it is. And so I think that it's a deficiency to approach the cross product operation that way. Because when you actually have to use it later on, and let's say your third year of calculus, again, you're using it, but you really don't know why things are happening the way that they are. And it puts you at a disadvantage for conceptually understanding what's going on when you use it for things like calculating divergence and curl and so on and so forth. Okay. So again, I'm going to spend a little time talking about what the cross product actually is. And if you've watched my dot product video or videos, then you should have some inkling of where I'm going with this. Okay. All right. So first, we want to recall that when we discuss the basic properties of vectors, that we did not have a binary operation that could be defined that will capture both the magnitude and rotational effects that come as a result of doing what we call vector multiplication. Okay. Now, the dot product, which I covered in my dot product video, is the vector multiplication that deals with strictly the magnitude effects of a vector acting on another vector in the same plane. Okay. Now, what the cross product operation does is that since vectors interact with each other and have both a magnitude and a rotational component to it, the cross product sort of embodies what goes on in that rotational component. Okay. And so we're going to talk more about that now. Now, in order to define the cross product, we'll have to lay some foundational groundwork, and that's what this first video is all about here. And we need to make some reasonable assumptions based upon how we want this particular operation to work mathematically. Okay. So we're kind of thinking about, all right, well, we know that this sort of thing happens in nature. So let's say if I'm looking at if I'm taking a screw and I'm trying to screw it into, let's say, some wood, and I know in doing that, I have to apply some force to it to actually, make it go down. But the more force I apply to it, the more it's actually going to go down into the wood as well. So there is a magnitude component of it, which is the actual force that's in the plane that I'm using to turn the screw in the first place. And then there's a rotational component that says that, hey, based upon what the magnitude of those vectors are and the angle in between those two vectors that actually makes the force to make the screw turn. Well, how fast is it going to turn and in what direction? Okay. So we need to think about when we see those sort of things, how we want to characterize that mathematically so that this operation does everything that we want it to do. Okay. Now, I will admit that I'm not going to give you a full-blown, in-depth discussion about the cross product, only because to actually do that, I would have to get way more abstract than what I want to. Okay. And for this level of mathematics, some of you that are watching this video may not have the mathematical training to actually understand some of the things that I'm going to talk about, and that's that is okay. Okay, at this level, you're not expected to have that, and so that is why in most textbooks, when they talk about introducing the cross product, essentially they just say, here's what it is, here's how we define it, here's how you use it, and they don't tell you much else about it. Okay, so that's the reason for that. But again, my approach here is going to be to make sure that you understand a little bit more about the motivation behind the operation, so that when you use it, you'll have a sense of what you're using it for. Okay. Now, because of the fact that I don't want to get too down into the weeds in an abstract sense here, I'm going to take this approach to these videos. And so I've already sort of said what the 3 videos I'm going to make and what they're going to entail, but I'm going to dig a little deeper into that. So in this video, we're going to summarize the basic concepts and properties of the cross product without proof. Okay, so that's what this particular video is about. In the next video, we're actually going to state what the cross product is and summarize the ways that it can be calculated, and then do several textbook examples. So this is going to be video 2. So for those of you that are just interested in that, you may want to turn off this particular video and go to the next one. Okay. Now, in doing those textbook-like examples, these are going to be all the things that I do examples of in that particular video. So video number 2 in this series. Then, of course, the final video, I will talk about constructing an informal proof showing how we actually state or how it is that we come up with the cross product being defined this way in terms of the sine function, and also how the magnitude of the cross product actually ends up being the same thing as the area of a parallelogram. Okay, and I'm also going to do a short proof in showing how we can use determinants to be able to do the cross product as well. Because again, in my opinion, I think it's important for you to kind of know where that stuff comes from, so that you have some sort of intuition of using the particular operation and knowing what its motivation is when you use it. All right, so the basic concepts of doing what we call U cross V. Okay, so we want to suppose that we have 2, and this is going to be preferably non-zero vectors in 3D space. The reason I say that, because if we have both vectors being 0, then there's not much happening. Everything ends up just being the 0 vector. Now, we're going to say that we want this cross product. We're going to call it a cross product, and we denote it as you've seen here. And the way that we'll say it is we'll say U cross V. Okay. Now, again, I'm using the vector notation where I have the arrows on top versus making the letters for the names of the vectors bold, just because everything's kind of the same color here. Okay. Now, we want this cross product operation to have the following characteristics. So number 1, we want the cross product is going to be perpendicular to the plane that this particular that these 2 particular vectors are in. Okay. Now, what I mean by that is this: the cross product of 2 vectors, we want that to actually end up being a vector as well. Okay. So if you remember with the dot product, what we did is we went from saying, hey, I got 2 vectors, we did some operation, and what we ended up getting is a scalar, okay, meaning a real number. Now, in this sense, we want a vector being quote unquote multiplied times another vector, and the result that we want to get is another vector. Okay, so that is one major difference in between the dot product and the cross product. Now, reason being for that is because, remember, we are trying to capture the rotational effect of what happens when a vector acts on another in a multiplication type of behavior in the same plane. And we know that whenever something rotates, it's going to rotate in a certain direction. And we also know that depending upon how fast or slow it rotates, it has some kind of magnitude. So that's why we want the cross product to end up being another vector. Okay. Now, we say here that both vectors u and v that are going to be a part of the cross product operation will have to lie in the same plane, just like how it does for the dot product. We also see here that the resultant vector, or the resulting vector, u cross v, will end up being perpendicular. Another way to say that is orthogonal, and another way to say that is it'll be 90 degrees apart from both u and v, via what I've stated up here. So if my corresponding vector result from doing the cross product is going to be perpendicular to the plane that both of these vectors are in, and both of these vectors, again stating that they have to be in the same plane, then naturally the cross product vector is going to be perpendicular to both of the vectors u and v. Okay. Now, you probably already know this if you're watching this video here, that whenever we do the absolute values on a vector, that stands for magnitude, or the length of the vector, and that's going to remain the same. Okay. Now, characteristic number 5, we want u cross v. This particular vector is thought of as a vector that describes the rotational effects of what happens when u and v are multiplied to each other. So I mentioned this earlier. This rotational effect can also, so this is like an alternative way we can think about it, can also be interpreted as a level of inclination of the plane that both vector u and vector v are in, and we want to say the level of inclination as that plane moves up or down. Okay, so basically what I'm saying is this: we know that whenever we have like a screw, and I'm not going to draw a very good screw here. So let's say we have this screw here, and we know if it, like for most screws, if you turn it to the right or do it clockwise like this, it's going to go down into the thing that you're screwing it into. Okay. So my point here is that if we think of, let's say right here, and I'm going to switch colors here just to kind of make this point. So let's say right here is the plane where the vectors u and v act upon each other. Okay. So in this plane, if we are applying vectors u and v such that we have this clockwise rotational motion, that is going to make the screw go down, like how I said. Well, what that's also going to do is make this plane go down. Okay. And so depending upon how fast or how much magnitude u and v have, that's going to dictate how fast or slow it goes down. But the main thing is that, hey, it's going to go down. So it's got a certain direction. If I am unscrewing or turning in a counterclockwise motion, then it is going to go up. And so the screw is going to go up. So that means this plane that's right here is also going to go up as well. Okay. Now, what gets interesting here is, let's say the vectors that I have are actually in this plane that are turned to the side. Okay. Well, we know that regardless of how the plane is situated, we want the u cross v vector to be a vector that's going to be perpendicular to this particular plane. Okay. So here when we talk about inclination, again, If we turn in one way, it's going to go up. If we turn in another way, it's going to go down. So when we say inclination, we don't mean how much it's inclined from, let's say, a horizontal like this. What we really mean is how much this plane, no matter how it's situated, is going to either go up or go down as we make those two vectors act on each other. Okay, so hopefully that made sense. But that is another interpretation of what the rotational effects do. And you may see that in some textbooks or some commentary about the cross product. So I wanted to make sure that I threw that in there. Okay. I personally just like to think about the rotational effects of it and not really worry about the plane aspect of it. But, you know, technically that's what's going on. Okay. Now, in saying all that, again, what constitutes as going up or down for this plane will depend upon, of course, the orientation of the coordinate system that we use and the direction that our vector u cross v will be in. Okay. And of course, when we say the direction of it, by definition, the direction of a vector is indicated by its unit vector. And that's just a vector divided by its own magnitude. Now, the next characteristic that we want is we want to make sure that there are no rotational effects that will occur if the vectors u and v are parallel to each other. Okay. So for instance, if I have some vector u here, and then I'll switch colors here for a second. Let's say I have another vector v, and these two vectors are pointing in the same direction, then of course the angle in between them is going to be 0. Okay. And if I have a vector act upon another vector, all pointing in the same direction, there's nothing that's going to make it rotate. Okay. Now, this could also be said if, let's say, I had a vector u, and then there is another vector v in the opposite direction. Okay. In this case, the vectors are going to act against each other, but nothing is going to make them actually have a rotating type of motion. So because of that, in both of these instances, both vectors u and v are parallel to one another. There will be no rotational effect whatsoever that's going to come out as a result of u acting on v or v acting on u. Okay. Now, if we had, let's say, a vector u here, and let's say another vector v here, then depending upon the angle in between these two vectors, there may be some type of rotational effect. Okay. Now, to show you why that would be, I'm actually going to draw a copy of this vector u and draw it down here. Okay. And so now when you see it this way, if this vector u is pushing upon this vector v at this spot here, you can imagine that the more that I push this particular vector here in the way that it's situated, the more it's going to rotate this way. Okay. And so, and just for differences here, let's say my vector u was like this on vector v. Okay. So if my vector u was acting like this and hitting vector v here, then the rotation would go this way. And so notice that when I come from down to up for u to act on vector v, then the rotation is going to be clockwise. But when I come up to down to act on vector v, the rotation is going to be counterclockwise. Okay. And so we want to make sure that that gets embodied in this particular operation. And so we know that in order to do that, of course, the vectors can't be parallel to one another. And that means they can't either point in the same direction or in the exact opposite direction. Okay. Now, with this being said, we know that we will have maximum rotational effect if, let's say, I have some vector u here, and then another vector v acts on it exactly at a 90-degree angle. Okay, so if that happens, then of course the way it's going to rotate, in this case, it'll end up being clockwise. It will rotate the most or the fastest, or however we are measuring that. But we know that they'll happen whenever we have a 90-degree angle in between these two vectors here. Okay, and so if you think of like a water paddle, if the boards of the water paddle are situated to where they're exactly 90 degrees apart, then you end up being able to move the most water, and thus having those paddles rotate the fastest. And of course, if that's for like on a boat or something like that, it makes the boat go faster, okay, with minimal effort. So we want to embody these 7 characteristics in this operation, okay? All right, and so I'm going to summarize these again just to make sure that we're thinking about them before we move on, because I know I've said a lot here. We want to make sure that the vector u cross v is perpendicular to the plane that vectors u and v are in. We want to make sure that we know that u and v actually have to be in the same plane, and because of that, the vector u cross v will actually be perpendicular both to vectors u and v. Okay, we know that we're going to be looking at the magnitude of the vector u cross v, and we know that although we can think of the vector u cross v as embodying the rotational effects of vector u acting on v, we also can think about it in terms of the plane and its level of inclination as it goes what we call up or down based upon the rotation that happens and in what direction. Okay, and then of course we want to make sure that there's no rotational effects whenever the vectors u and v are parallel to one another, and we want to make sure that there's max rotational effect whenever vectors u and v are perpendicular to one another. All right, so the operation that we come up with has to embody all of that. So based upon those 7 characteristics, we know that we need this cross product operation to have. We're going to establish some basic foundational assumptions to summarize how the cross product should work. Okay. Now, what you see above you here, figures A and B, is basically the construction of the cross product u cross v and how we actually think about it. So notice that vectors u and v are in the same plane, and I'm looking at figure A here. They're in the same plane, vectors u and v. The vector u cross v actually shoots out based upon the fact that u is acting on v. And of course it has a direction, and we're using what's called the right hand rule to be able to characterize that. Now, please note that there's a right hand rule, there's a left hand rule, and there's several other rules that you can come up with. Okay, so and we're going to talk a little bit about what that actually means in terms of the u cross v vector. But the main thing here to know is that whenever we have a vector acting on another vector in the same plane, depending upon the angle that's in between those two vectors, that's going to constitute some kind of rotational effect. Okay, and so notice that here when u acts on v, that the direction of the u cross v vector goes up according to the right hand rule. But when v acts on u, then the direction of the cross product vector goes down according to the right hand rule convention. Okay. All right, so we want to make sure that we're aware of that. Now, because of the fact that depending upon whether u acts on v or v acts on u, this vector that we've been calling the cross product of u vectors u and v, or u cross v, is actually what we call a pseudo vector. Okay, so it's not actually quite like a real vector. We call them true vectors or polar vectors. What a pseudo vector is a vector that lacks either lacks a combination of, I should say it that way, magnitude and direction that is unique regardless of the coordinate system that we use. Okay, so that's essentially what a pseudo vector is. In the case of the cross product, the issue is that the cross product doesn't have a defined direction. Okay, the magnitude of the cross product will be what it is, but depending upon the orientation of the coordinate system, or in this case, is u acting on v or is v acting on u, depending upon which vector you make act on the other will depend upon the direction. And that's kind of a problem. It's not one that we can't overcome, but what it does is it makes some of the properties that we would like for this vector operation to have not be as clean as we like. And so we have to account for those differences there. Okay. Now, of course, in here in the notes, I talk about this whole thing about the left-hand rule versus the right-hand rule. And of course, if we did the left-hand rule, this would look exactly the opposite. So if you took this particular graph here, and let's say you rotated everything. So we took these two graphs here, and we actually just turn this upside down. And we use a left hand instead of a right hand. That's exactly what the left hand rule would end up looking like. Okay. All right. So with that, again, the main point here is that u cross v is not a true vector, aka is not a polar vector, because it doesn't have both a unique magnitude and direction. And so when I say that, again, I mean that the combination of magnitude and direction put together is not unique based upon the coordinate system orientation. All right, so again, here's me formally stating the definition of a pseudo vector. It is a vector that does not have a unique magnitude and direction regardless of the coordinate system orientation. That's essentially what it is. And to go a little deeper here, again, we know that u cross v fails to be a true vector because of the fact that it doesn't have unique direction. So I've already talked about that. And again, we saw how when u acts on v, how the direction of the normal vector, or that u cross v vector, is shooting up out of the plane, whereas if v acts on u, then it's shooting down from the plane, okay, or down into the plane. Okay. Now, basically what's happening here from an algebraic standpoint is that the notion of an operation being commutative is not clean. Okay, so for instance, if our u cross v vector was a true vector, then this particular linear property would be true about it. Okay, now in terms of putting in everyday language, if u cross v was a true vector, if we think about real numbers, then we would say 2 times 3 is the same thing as 3 times 2. Okay, and that thing would always happen. But because of the fact that in the world of vectors, 2 times 3 is not actually the same thing as 3 times 2, this whole notion of the cross product being purely commutative in the way that we understand it for real numbers doesn't happen. Okay. Now, thankful for us, in the world of vectors, 2 times 3 looks like negative 3 times 2. So, and of course, signs, when it comes to vectors, only means direction. So we're okay with actually having that that small aberration there. Okay. Now, another way of stating the fact that, hey, this commutative property is under cross product is not a pure one because of direction is we could show that if vectors u and v directions were both switched to its opposites, then the direction of the resulting vector u cross v would fail to switch directions as well. And so figure C sort of shows that. So if you look at our vector u and our vector v here, of course, when u acts on v, the rotation is going to be clockwise. Okay. Now notice that if I switch the directions of u and v, and then I make u minus u act on minus v, notice that it's spinning in the same direction as it was if I had u acting on v. Okay. And so if this whole commutative property under cross product would work purely just like how it does in the real numbers, if I switch the direction for both of the vectors, then that means that the direction of the cross product should switch as well. So I should get something like, minus vector u cross minus vector v would end up being minus vector u cross v. So that's what it should be if the commutative property held in the way that we know it. But since it doesn't, then we have to account for that. And again, not a huge offense, but it's one that we do have to take note of. All right, so at this point in our discussion about the cross product, what we have gone over is sort of the basic thinking about, hey, if we want to create this cross product operation, what do we want it to do? We've talked about some ways that we can interpret what's going on from a rotational standpoint or plane inclination standpoint. And we've also clarified the fact that this u cross v vector that we're talking about is really not a true vector. It is what we call a pseudo vector, because although it has magnitude, that's going to be what it is. The direction of it is subject to debate of how you orientate the coordinate system that you're going to use, and whether you translate in your mind that vector u is acting on vector v, or vector v is acting on vector u. Okay. Now, other things that we need to think about is what's called pairwise cross products for fundamental unit vectors. Now, basically, what I'm getting at here is whenever we are dealing with unit vectors, and I'm going to deal with the most fundamental ones, our I, J, and K unit vectors that we've seen before. Whenever we deal with those, we know based upon how the cross product is supposed to act, what the outcome should be. Okay. Now, just as an example here, and let me switch colors. So what we're saying here is that if I wanted to take some unit vector I and I wanted to cross it, do the cross product with it with another unit vector J, and just to make sure that it's clear here, the vector I in 3D space looks like this in component form, and the vector J looks like this in 3D space in component form, and the vector K looks like this in 3D space in component form. Okay. So if I do I cross J, then the result ends up being K. And if you think about it, this makes a whole lot of sense. Here's my vector I. Here's my vector J. And of course, note here that vector I and J are going to be in the same plane. Okay. To make that look a little bit more convincing here, I'll go ahead and draw the parallelogram and show you that they're both in the same plane here. So here, if I draw this parallelogram, then of course I and J are on the edges of this particular plane, okay, or the snapshot of the plane. Notice how the unit vector K is jumping out of that particular plane on the edge there. And on top of that, also note that K is perpendicular to J and K is perpendicular to I. Okay. And so what these pairwise cross products help us do is to be able to simplify our computation whenever we use it. And again, I, J, and K are all perpendicular to each other. So that means that the result of taking two of those unit vectors and doing the cross product with them is going to yield another vector. Okay. Now, sticking with this example here, notice that whenever we say I cross J, the interpretation is that the vector I is going to act on the vector J. Okay. So if I take that interpretation here, then one of the things that I'm going to do here, so I'm going to switch colors again. I'm going to use, let's see, I'll use blue here. So this vector J can also be moved here. And again, I'm just making it real fat and big so that you can see it, although I didn't do a very good job there. So let's try again and make it a little bit more intelligible. So this is vector J here. Okay. And so if I really think about what's happening, if I is acting on J, and this is J as well. So if I is acting on J, it's going to make this whole system kind of turn this way. Okay. And of course, if it's turning that way, in the orientation of how we have everything set up, when it turns in a counterclockwise motion, we're going to be going upward. Okay, according to how we have this coordinate system set up, and of course, upward is exactly what K is telling me. Okay. Now, if I have it to where, let's say I do the reverse, okay, meaning instead of I acting on J, J acts on I, then of course the direct opposite is going to happen. Okay. So what's going to be going on here is that if J is acting on I, then I can move this vector I here, and now the rotation is going to go this way, which is clockwise. And so according to what we just seen, if counterclockwise is making my vector K go up, then clockwise is going to make my vector K go down. Okay. And so that is essentially what these pairwise cross products are trying to get you to see here. And this is a basic function of how our cross product function should act. Okay. Now, I've drawn these graphs here to kind of help you remember, well, what's going to be the outcome whenever we use these fundamental vectors here. And so, for instance, let's say I want to do J cross K, right? Well, if I do J cross K, the result is I. Okay. If I wanted to do K cross I, then I start at K, I do KI, and then I move to the next one. So K, let's try that again. So K cross I is going to lead to J. And of course, the opposite is true as well. So if we go from I to K here, just imagine if we are going in the clockwise direction now. So I'll erase this. So we see here that I cross K will go to J, but it will go in the opposite direction. Hence why we put a negative on there. And so that's why I made this additional pairwise cross product graph with the negatives on there to make sure that you get, hey, whenever you're spinning in a clockwise motion, the result is going to be negative vector. But if you spin in a counterclockwise motion, counterclockwise motion this way, then your vector is going to be quote unquote positive. Okay. All right. Now, in taking into account of that, remember that let's say a vector I, if I cross it with itself, it's going to be pointing in the same direction. So that means that the result of that should be the 0 vector. If I was to take the opposite of vector I and cross it with I, then of course these are going to be pointing in opposite directions, and again should end up being the 0 vector. So that holds for plus or minus I cross I, plus or minus J cross J, or plus or minus K cross K. Okay, and so we know in all these instances we'll end up getting the 0 vector. All right, so another thing that we need to think about is we've already seen how the cross product is going to be defined in terms of a sine function. And so now we need to talk about, well, why is that? Okay. Well, if we recall, vectors that have the same direction are going to have an angle measure in between them of either 0 degrees or 180 degrees. Okay. The angle measure of being 0 degrees in between the two vectors if they're going in the same direction, 180 degrees if they are going in the opposite direction. Again, if you want to talk about it in terms of radians, we can just say 0 radians or pi radians, okay, respectively. Now, because of the fact that anytime two vectors have an angle of 0 or 180 degrees in between each other, we want the rotational effects to be 0 because there won't be any. The sine function actually provides that functionality for us. And so that's why it's acceptable for us to be able to express the outcome of u cross v in terms of a function of sine. And really the sine of some angle, that's going to be the magnitude part of it, okay? So similarly, we know that if we have two vectors that are exactly 90 degrees apart, or let's say they're 270 degrees apart. So let's say we have a vector like this, and then we have another vector going in this direction. That's 270 degrees there. But realize that that's still 90 degrees there. So we really won't consider this one, but I just threw it in there just to make sure that, hey, if anyone has a question, we could actually consider it that way. But the reason why we would only look at 90 degrees is because if you remember from the dot product, these angles that are here, that angle comes from an angle that is part of a triangle. And we know that the sum of all angles in a triangle have to be 180 degrees. So it really doesn't make, it doesn't make a lot of sense, but we could actually use it if we wanted to have angles that are out of the range of 0 to 180 degrees, okay? But either way, you could also translate 270 degrees as negative 90 degrees, okay? So it still ends up being perpendicular either way. So because of the fact that we want the cross product to be able to have a situation where it's going to be at most, the magnitude is going to be the most, whether it's in the same direction or opposite direction or whatever, from a perpendicular standpoint. Sine theta being plus or minus 1, that only occurs at these two angles whenever we're considering in between 0 to 360 degrees. So again, just trying to round out everything to make sure that you understand why it makes sense for us to use the sine function in defining the cross product. Okay. All right. So Let's go ahead and wrap this up. So now that we've talked about all that other stuff, the sort of embody what this cross product thing is supposed to be like, we know that because all the vector operations, including the cross product, needs to preserve linear properties for the vectors to act correctly like how we want, then that means that certain things that we've established in my earlier videos on just vector basics, like vector addition and scalar multiplication, actually holding within the world of vectors, that's going to have to follow suit here for the cross product. Okay, so the cross product is going to be standing on the shoulders of vector addition and scalar multiplication to be able to do its thing. And so it still has to be able to function and still have linear properties here. So what I'm doing here is I'm actually stating what most textbooks will give you to say, hey, if you're using a cross product, these are the basic rules that the cross product goes by. Okay. And so here, if we let u, v, and w be vectors, whereas components are composed of real numbers, and if we let r and s be scalar values, then all these properties that I state here are true. Okay. Now this first one just basically says, if I started off with some vector u and some vector v, and I wanted to increase the length by a factor of r for this one, increase the length by a factor of s for that one, and then do the cross product for both of those vectors, then the resulting pseudo vector u cross v should be, its magnitude should be enlarged by a factor of r times s. That basically is what that says. For property b, is just basically showing you that the cross product is able to be distributed over vector addition coming from the left. Okay. The property D is showing you the same thing as property B is, but you're coming from the right. And we need to show that because of the fact that we don't just assume that the distributive property works the same on the left that it does on the right, because we don't assume that multiplication acts the same on the left that it does on the right. Of course, we want it to do that. And of course, when it does, we want to make sure that that's stated. But for instance, like matrices, we know that if we multiply, let's say, two matrices A and B, that's not the same thing as B times A. So again, the fact that this doesn't always work, that A times B is equal to B times A, is a reason indirectly to say, well, hey, we need to check out this, distributive property as well. Now, property C here is the one that's very important to us, because that lets us know that U cross V is not necessarily equal to V cross U. Okay. And of course, it differs only in the direction in which that pseudo vector that's going to be perpendicular to the plane that U and V in go. And so, of course, we have to make note of that. Now, of course, these last two properties are relatively simple. Of course, E just says that the zero vector crossed with anything is going to be the zero vector. And here in this case, we see that if I have some, some vector V cross W, and I take that result and I cross it with another vector, this is actually what it ends up being. Actually end up being the difference in between two vectors here. So another way of saying this is that if we cross V and W together and then have U act on that result, what we end up having here is a vector that is a linear combination of both V and W. Okay. Now, my note here is that since U cross V is a pseudo vector, it's actually a pseudo vector because U cross V doesn't have a unique direction. Of course, we talked about all that. And because of that, technically, the commutative property fails, but since it's only direction, it's like, oh, okay, not a big deal. In the world of vectors, signs just means direction, and that really doesn't matter too much. Okay. All right. So at this point, I'm going to stop this particular video because I've already covered all the foundational things that I want to cover. In part 2, or the second video, I'm going to start on this page here, and we're actually going to define what the cross product is, and you can kind of see it there. And we're going to talk about some applications where it is used, and then we're going to go over some examples. And then, of course, the final video will actually do the informal proofs for how we can actually even state something like this in the first place, and how we're going to see that U cross V can be calculated using determinants.